For this video here, we'll look at the k-nearest neighbor algorithm. We'll apply that model in two different ways. That is from the scikit-learn neighbors. We are going to use the remaining ones under here of train test split, standard scalar, as you need to standardize your data, classification report, confusion matrix, and we'll plot it with Seaborn, which is referred to as SNS in our code. So for k-nearest neighbors, what it will do is it tries to group by looking for the nearest neighbors. And you tell it how many nearest neighbors to use for that. So if you say, look at my two nearest neighbors, it's going to plot you with them. So that's how it groups. Yes, it is used on structured or data sets generally, or supervised. It is a supervised learning model. I'm going to create it to excuse me, a supervised sort of learning format with this. But first, I want to show you why you can't use it on a unsupervised data set. It's going to look really bad. But I can make this into a structured data set. You need one known class or one column to be known. And I will set that in the second example. But let's see. So here we're reading the same data set. This one I'm just going to actually comment out that it's okay to say that. We're going to standardize the data set. This is one of the terms to look up research for the week is scaling or standard scalar. You want to make sure you look at that. It is in the overview. Let's see, make sure I put that there. Yep, I got scalar down on your list of terms to might want to research. So we're going to, remember you need a known class. So we're pretending that row 2 is our known class. So you drop it out and then you fit the scalar against the remaining columns, features, or dimensions. And we know that because the axis is set to 1. Axis to 1 is columns, axis equals to 0 is rows. So we fit it on the remaining columns. We just happen to have 2 here, which is fine. So it's going to fit on row 1 or apply the scalar algorithm to that. So this whole part is to do that, we fit the scalar, and then you have to transform, which technically does the dimensionality reduction. And then we get back what is a NumPy array, and we could do a type on that to see that. So we need to convert that NumPy array back to a data frame, which is what we're doing here. And that data frame, again, is not going to use our known class because that will give you overfitted data. It will certainly give you good results if you include your class into the training data. So we're taking our scaled features, NumPy array, and we're again dropping the column or known class that we have. And we're creating a scaled data frame. We're using the scaled data frame as our X variable. We use row 2 or our known class as the Y variable. We do our train test split. Notice test size is set to 30%. We'll go to the test variables here, and 70% will go to the train variables. And then we're going to set or create our k-nearest neighbors model, which is called k-neighbors classifier, and we're setting the nearest neighbors to 20. It's a guess right now. We don't know how many to use, but we can use error rating to determine the number to use if we wanted, and we'll do that later. So we're applying it. We're using the 20 nearest neighbors as our grouping mechanism. We have the model. Now we're going to fit the model to our known training data, the 70% of the data set, and we're going to predict on the X test, and we're going to get our prediction class, And from there, we have our Y-test and our prediction class. We can do a classification report. We can do a confusion matrix, all of which can tell you how well the data is or what predictions it's making. And then we can plot it as a heat map using the Seaborn library. And that's what this confusion matrix is being plotted as. C maps the colors. This just pretties it up. So when it runs, you can see this is the confusion or the classification report here is printed here. Something you can look up and see what that means. The precision's the important one. And then you have a heat map, which I will show you. And this is why you can't do k-nearest neighbors on an unstructured data set. So it takes it a bit, but here's the k-nearest neighbors. Because what it's going to do is it's going to make a prediction of everything. So we have numbers from 1 to 100. You're going to get them on your X, Y. So if anyone here predicted 84, it shows you the value it got. Some of them are 32, 48. So it didn't do very well. This isn't a good confusion matrix. So we'll get rid of this. And that's why you have to do this k-nearest neighbor on a structured data set. So we'll convert it to a structured data set by adding a known class of which we're creating a new row called binary. And we're going to set where everywhere where row 2 is greater than 50 in the binary column, we'll write a 1, and everything less than 50, we'll write it as a 0. Now this isn't perfect for this. Again, this is an unstructured data set. And my attempt here is to convert it now into a structured one by really having a known class called binary. So I change all these to binary because I don't want them in my data set when it does all the fitting and transforming, because it will drop that out. And now there's a row 1 and row 2 that it will run this on. And then I use binary here. So now I truly have a known class. It's not random. It's going to be a 1 or 0. I'm fitting while dropping that, and then I'm dimension reduction through the transform by dropping it. And then I'm going to convert that NumPy array into a data frame by dropping my binary. I'm going to use the new scaled data frame and the binary column as my Y. Same train test split, same k neighbors, and same everything. So let's see the confusion matrix now. Print it out as a heat map. So you can see this is a little better. Your binary, so you have in the 0 column, it was right almost every time except for 1. So these are true positives where I said it was going to be. I predicted a 0 and it actually was a 1. And this is one where I said it was a 0, but it was a 1. So one time I was wrong. And on this one, I was right 100% of the time. Well, big time overfit. It shouldn't be that good. But again, I took a big chunk of random data and converted it into a 1 and 0. So it does pretty good in terms of that. But it looks way better. So that's why you want it on a known class. And we'll do the error rate next. So again, k-nearest neighbor does group, and you do set the number of nearest neighbors here, right here, there. So it's grouping based on nearest neighbors, but you can figure out which number of nearest neighbors to use by doing looping through and getting the error rates, which is what this does. Since I have from 1 to 100, I use the range from 1 to 101. Again, it does 1 through 100. Again, I have my list that I append to. I'm going to create a k-nearest neighbors using I, which is going to be in the for loop. It's going to be the numbers 1, then 2, then 3, all the way up to 100. It's going to fit. It's going to make predictions, and then it's going to get the error rate by taking the mean of the new predictions, as long as it's not equal to X test. Otherwise, that's the same. And then I'm going to plot the new one. So when you look at the error rate, you can use the error rate model to determine the number of neighbors to use. So you want to use the lowest value since there's several of them pretty close. I think 10, around 18, 22, 24 are all good values to use. We used 20, so that was probably way up here, not a great value. Could have used like 18, would have been a better value. Or even less, nearest neighbors here would be a variable. So what you're looking for is the lowest error rate, which is the low values here. Use one of those as your number of nearest neighbors. So that's all I wanted to show for k nearest neighbors.